Welcome to Module 3. This module focuses on ocean basins, so the actual containers that the seawater sits in, as well as the sediments associated with the ocean. In the first part of today's lecture, we'll focus on ocean basins, how we go about studying these ocean basins, what do they look like in specific parts of the ocean basin. Then we'll move on to talking about sediments associated with the ocean. What are these sediments? What is a sediment? The different types of sediment that can occur, as well as how do we take a look at these sediments and study them. How do we know what ocean basins look like? How do we know what the ocean floor looks like? Remember, these are areas in the earth that are covered by 2 to 3 to sometimes 7, 8, 9 kilometers of water. So how do we know what they look like? Well, ideally, in the perfect world, what we'd be able to do is we'd go and directly examine it with our own eyes. But we see there's other methods that we use to examine the ocean as well, the ocean floor. And these might be as far ranging as satellites orbiting the earth, or more indirect methods closer to their surface, such as sonar. So one method of looking at the ocean basin, looking at the ocean floor, is by direct examination, as we said in the previous slide. So this involves either going down, either snorkeling or scuba diving and examining the ocean floor, or in greater depths where we might not be able to scuba dive to, using remotely controlled submarines or manned submarines, submersibles. So we can go down there, we can collect samples, we can take readings, we can take pictures, we can take videos, and gather together a wealth of information about the ocean basin, about the ocean floor. So this is one way of looking at the ocean floor, but there are a couple caveats to it. Number one, it's expensive. It costs a lot of money to maintain these submersibles, to build these submersibles. The other thing is it's dangerous. Once again, you're traveling to these areas of the earth that are inhospitable for human life. You're underwater, there's tremendous pressure, changes in temperature, and the fact that we can't breathe air down there. So we find that with submersibles, there are limits to where we can explore and how deep we can explore. We can't visit everywhere in the ocean. We can look at some examples here, and this gives you sort of the depth, or maximum depth, that most manned and unmanned systems can operate at. There are some exceptions, for example, the Trieste or the Deep Sea Challenger. Those have been able to go deeper. But we find that a small percentage of the ocean's floor, especially when we get into deeper water, cannot be explored by the use of submersibles, either manned or remotely controlled. So this brings us to the subject of bathymetry. And bathymetry can be thought of as one of these scientific subdisciplines. And basically what you're looking at is you're looking at submarine topography, the shape, the morphology, the relief, differences between high points and low points, and the depth of underwater terrain. So something that is done remotely, you don't actually have to get down there to the actual terrain, the seafloor, to look at it, but allows us to study the ocean floor, the contours. Where do we have valleys? Where do you have mountains? Where do you have hills? Are they steep? Are they shallow dipping? It allows us to measure how deep the ocean is in certain spots. So instead of like how they did for the Challenger Deep when they first discovered, or the Challenger expedition when they first discovered the Challenger Deep, we're basically putting a rope overboard and measuring how much rope went out. It allows us to quite scientifically and quite accurately measure the ocean depth. From this, we can develop bathymetric maps that give us a idea of what the ocean floor looks like, and we can see variations in relief, variations between low points and high points, and quite often to make them able for oceanographers, scientists, to understand them, we color them and we use contour lines to show these changes in elevation below the sea surface. As we'll see, the methods by which we study the ocean, especially modern day methods, only developed recently within the last 100 years or so, or even less than that. For the longest time, the main way of studying the ocean floor and seeing variations in the height of the ocean floor was using rope. We see that Posidonius back in 85 BC carried out some of the first bathymetric studies along the Mediterranean Sea. And what he basically did is he took a rope with a stone tied to the end of it. He had roughly 2 kilometers of rope, or it would be 2 kilometers of rope. This is called a lead line. Went out in a boat, dropped it overboard, measured how much rope went out, and from that he could determine the depth at that point. You do it in a number of different places along a particular area of the ocean, or in this case the Mediterranean Sea, and you can get a rough idea of what the ocean floor looks like. Is it all flat and level, or is there hills, or are there mountains, or are there troughs, canyons, or valleys? So this is a method that was used for thousands of years. Literally still in the 1870s, as I said, when the HMS Challenger carried out their scientific expedition, they took a number of bottom soundings or depth soundings. Soundings is what we used to call like when they measure from the surface down to the bottom of the ocean floor. It took 492, just if you're interested in it. And It worked, but there are a lot of potential problems with this method. One of them is time. It takes a long time to lower a rope and raise a rope, pull it back up. So there's this whole issue of time. Supply of rope. You better make sure you have enough rope on board. What happens if you run out of rope? Well, you can't complete that sounding measurement. And the other thing is the type of rope, because rope will stretch over time. So some rope might stretch a little bit, some rope might stretch a lot, and this is going to give you an erroneous reading as well. So this method still worked. I mean, the Challenger Deep did find this, or the Challenger expedition did find the Challenger Deep, but it wasn't the most accurate, time-efficient way to determine how deep the ocean. It wasn't until 1914 that a new method started to be developed, so a little over 100 years ago. And this is a method that formed part of what was called the iceberg detector and echo depth sounder, developed by a guy named Reginald Fessenden. And what it was basically was a device that was used to send underwater signals. And those underwater signals would be sent out. If they would hit an object, they would bounce back. That sound wave would bounce back, basically an echo, and then the machine would record that echo. You can see the gentleman on the image on the right is holding one of the oscillators that used to measure this sound bouncing back, and from that they were able to determine objects underwater. So this is actually working right now in a horizontal manner. So they're sending that sound wave, that pulses sound, out horizontally through the water. This is the first practical form of what we know as shipboard sonar. And the reason why it came about, why was this developed? Well, I think the fact that we call it an iceberg detector is an important point, because if you look in the history, a couple of years before that, so 2 years prior to the development of this iceberg detector and echo depth sounder, was the Titanic sinking. So this happened in 1912. The Titanic, if you're not familiar with it, the ship that was sailing from England to North America, was supposedly unsinkable. It struck an iceberg, tore a huge hole in it, and the Titanic sunk, and many people lost their lives as a result of this. So there's this big push on since the disaster in 1912 to be able to detect the presence of icebergs underwater. So how did this work? How did the iceberg detector and echo depth sounder work? Well, what happened was a ship would send out an underwater sound pulse. We talked about this a couple slides ago. We saw a ship, we saw the speaker, the oscillator basically picked up the sound, and the thought was the sound pulse would be projected ahead of the ship. It would hit an object, in this case an iceberg in the water, and it would bounce back. So the sound pulse bounces back. It basically echoes back to the ship and is picked up by the ship's detector. Now, keep in mind, this is all happening sort of horizontally in the water. So the pulse goes out in front of the ship, hits the iceberg, is returned, that sound pulse bounces off the iceberg and echoes back to the ship where the sound is picked up. And from that, they're able to determine the distance to the iceberg and what is underwater and if it is a danger. So then the next question is, what happens if you take that pulse, instead of directing it outwards from the front of the ship, direct it downwards? And what you see here now is you'll still get the same thing happening. That pulse of sound is directed downwards. It's going to hit the ocean floor, some object on the ocean floor, bounce back up where it's picked up and recorded by speakers within the ship. So this is the development of the first echo sounder. We see it being used by a ship called the German Meteor in 1925 to 1927. Traveled across the Atlantic Ocean a number of times, showed the presence of the Mid-Atlantic Ridge. So it proved to be very early on a quite effective method by which we could map and look at the ocean floor. So here we have a picture of a very basic echo sounder. So once again, the sound beam or sound wave is directed down towards the bottom of the ocean floor, and then it bounces off and is reflected back to the ship, usually at some sort of angle, as you can see here. Very simple formula used to figure what the depth of the water is, or the depth from the surface to the ocean floor. You take the velocity at which your sound wave is traveling at, multiply that at the time divided by 2. Once again, this isn't a formula I would expect you to remember, but just to let you kind of get a sense of how this process works. To the left of it, we see in that little square there a picture of a very typical sort of image that would be developed from an echo sounder, and you can see not very, distinctive. You can't get really great detail, but you get the sense that there's this little valley, area of higher elevation, goes up a little bit, the seafloor, dips down, and then starts to rise up again. So it gives you a very crude idea of what the seafloor looks like, but once again, a lot better than what was being developed from letting a rope fall overboard and measuring the length of rope that went out. So as mentioned earlier in the lecture, by 1925 to 1927, the German ship, the Meteor, went out, traveled across the Atlantic, took about 14 profiles, and started to really develop a picture of what the ocean floor, at least in the Atlantic, looked like. This was preceded by 1922, where the first continuous profile across an ocean basin was developed. So this is revolutionary at the time. Instead of having the odd little reading here and there, we actually got a picture of what it looked like if we traveled from one point A to point B across the ocean, and discovered if it was like a flat ocean floor, if there's variations. And once again, it was the German ship Meteor back in this sort of sampling or this measuring mission between 1925 and 1927 that really confirmed the presence of this mid-Atlantic ridge. We're going to take a little detour here and talk about Marie Tharp. Marie Tharp lived from 1920 to 2006, and she was a geologist, and more importantly, she was an oceanographic cartographer. She's probably one of the top map makers of the world. And she created one of the first scientific maps of the Atlantic Ocean floor, her as well as a partner, Bruce Hezine. Marie's story, you don't hear much about her. When you look at some of this early work and what the ocean floor looked like, she wasn't allowed to go out on ships. It was believed she was bad luck to be on ships because she was a female. When the first maps were being published that they developed, her and Hezine developed of the North Atlantic, her name didn't show up on it, but over time she starts to get more and more recognition. What she did is she took this data that was being collected by ships like the Meteor and their subsequent ships after that, took that data, and you can see an example of some of the data on the upper right-hand image there, and developed this really detailed, excellent image of, first of all, the Atlantic Ocean. She used this and said, yeah, I think Wagner actually had something, was onto something with continental drift. Hezine didn't believe in continental drift, but she did. She helped prove that mid-ocean ridges existed, and she created these beautiful maps of the ocean floor that gave us a really good, sort of the first initial look of what the ocean floor would actually look like. What she eventually developed was this map here, a map of the world's ocean floor. And even today, in 2019, it's considered one of the definitive maps of the ocean floor. One final note before we move on, this was all done by hand. So this is a time before computers, before you could use programs like Adobe Illustrator or AutoCAD. Marie Tharp did this all by hand using scientific data and her partner as well to create these beautiful maps, detailed maps of the ocean floor. And this is sort of the first picture that people could get of what the ocean floor looked like. Before it was sort of like, okay, it's probably this big smooth basin. But she helped to prove that there were all these different physiographic features of the ocean floor. There were hills, mountains, valleys, things like the ridges that were essentially underwater mountain chains. So back to the echo sounder. Still an improvement of you looking at the ocean floor using a rope with a rock tied to the end of it, but still getting inaccurate readings. And one of these reasons is because you're using a single beam. And what happens, depending on where you're measuring or what the ocean floor looks like, is that the beam that bounces back can actually give you a measured depth that's less than the actual depth. And that's due to a number of different reasons. Contour error when depths are great. The sound reflects off a great area of the seafloor, so the reflective cone gets bigger, you get an error introduced with that. Changes in the ship course can affect the data. Water depth, if you all of a sudden go over this small submarine canyon, you get this example that we see in the right-hand side. Or even changes in the water itself. Physical change in the water can cause minute change in the velocity, which will affect the readings that you get. But still, using the single beam echo sounder technique, a much, much more accurate way of looking at the ocean floor than what had previously existed. How do you solve these problems? Well, basically you add more beams. Instead of just directing one beam down, you direct many beams. In the 1960s, the multi-beam echo sounder was developed, having up to about 121 beams pointing down at the ocean floor, covering about a area at a 120-degree arc, a right angles to the direction of travel. And what happened is this gave you a much more accurate picture of the ocean floor and took away some of those errors that occurred when you're using just a single beam technique. This also meant using a multi-beam echo sounder that you could map the ocean floor quicker. So now instead of going and just taking one transect or one profile across the ocean floor, you could cover a wider area using something very similar to mowing the lawn. You you move the ship around, you basically mow the ocean floor. But even this has issues with it. Basically time. The ocean is covers a huge, vast expanse of the world's surface. If we use this technique, it could take up to 125 years to map the entire ocean floor. Not very practical if we want to know what the ocean floor looks like. Here we have an image of the seafloor near the East Pacific Rise. East Pacific Rise is a mid-Atlantic ridge. We can see sort of, we have ships there, but we're still getting uneven, patchy coverage. There's areas where ships converge. There's areas where the ship might, path might be apart. So you don't get complete coverage. The other thing I just want to note at this point, by this point now we're using computers. So the computers take the data that's generated by this echo beam sounder. And what it does then is it takes it, it analyzes and generates images such as this with different colors representing different elevations. What we have at this point is we see that advances in technology moving from just a ropes thrown overboard to the echo sounder, the single beam, and then to the multi-beam sounder means that we start to develop a better picture of the ocean floor and see more and more of the ocean floor. But we're still not getting a great picture of the ocean floor. So now we're going to look at a couple other advances that even further refine what we're seeing on the floor of the ocean, how the ocean basins look. The goal is to be able to map the ocean floor quickly with great accuracy. So this led to the development of the side scan sonar. In this case, instead of the sound pulse being generated directly at the ship, it's being generated by something called a towfish, which is this piece of instrumentation that's pulled behind the ship. What happens is the pulses get sent towards the sea floor. They're sent to cover a wide angle, a wide area, and they're sent down perpendicular to the path of the sensor. So the ship's moving in one direction, pulling that towfish in one direction, where you have this one direction. And what's going to happen is the pulses are going to be sent down perpendicular to that. We can use this with a single beam echo sounder. We can use it with a multi-beam echo sounder. But the key thing here is that we increase the coverage. We're covering a much larger area than we were before. The beauty of using the side scan sonar is not only does it allow us to cover a greater area, but it also provides greater resolution of what features on the ocean floor look like. So areas that are harder, like the areas made of rock, reflect more sound, have a stronger, longer return signal, so that signal that's received by the ship is stronger. Areas that might be covered by sediment have a much quieter return signals. What we also see is even changes sort of in the color. So areas with louder echoes, where they have that, that hard thing will have sort of created in the process data a darker area, whilst areas that are softer will be quieter. The other thing is it can look and pick up shadows by objects on the ocean floor. So if you have something, for example, like a boulder laying there, as you'll see in the next set of slides, things like ships or shipwrecks, even human bodies, it can detect a shadow and from that obtain the size of that object that's making it. So using shadows, using the return signals from harder and softer material, you can obtain very detailed images of what is going on the ocean floor. These are just some images, a collection of images obtained through side scan sonar. We have up in the upper left the continental margin, which we'll be talking about in a few moments. Then we see some other features here, shipwrecks. You can also find downed airplanes, as well as a whole host of other objects found on the ocean floor, both man-made or naturally occurring. Those are some methods of looking at the ocean floor and discovering what the ocean floor looks like. There have been improvements over the years, but we still find that we're not getting as great of detail as we'd like, and it still takes a long time to obtain all this information. So now we're going to move into the area of remote sensing. And what remote sensing is acquiring information about an object. It could be land, it could be a city, it could be the ocean, but you acquire that information without actually making physical contact with what you want to get information about. So for example, anyone who flies a drone, takes pictures with a drone, you're using a form of remote sensing. You're looking at the earth from above, but the thing that's taking the picture isn't in direct contact with the earth. Airplanes can do the same thing, and then even now we have satellites that have sensors aboard and they can collect data, and basically what it does is it's collecting data from energy that is reflected from the earth. We're not going to worry about drones, we're not going to worry about information collected by airplanes, but we're going to look at a form of remote sensing known as satellite altimetry. So you're not measuring the ocean depth directly, but what happens is satellites that are orbiting the Earth are measuring small differences in sea surface height. Everything has a gravitational attraction. So even you sitting here listening to this lecture, you're creating a small gravitational field. Because you're small, the Earth is so big, nothing is really in sense of gravity attracted towards you. But we can't determine it, but the satellite actually can determine it. It can determine over areas where we might have mountains over the ocean. There's greater amount of gravity. It's a larger mass of these undersea mountains, so there's a greater mass associated with them, so it does have a slightly greater gravitational pull. what we'll see is there's slight variations in sea surface height. And it's actually the satellites that pick up these sea surface height variations, and then those are translated into different elevations on the sea floor. Let's take a look at the data that's collected by multi-beam echo sounding. So here's an area of the South Pacific seabed. You can see some areas with higher elevations show up as sort of those green little blotches. Now we're going to take a look at an example of data collected from a satellite. Here we go, same area with data collected from a satellite. So once again, this is data that's been processed. It's not the raw data. So it goes through computers, a number of different mathematical models, and it ends up with this image that we see here. But the important thing is you can see that this is much clearer. We get a greater definition of features. We see very clearly where we have these high little things that we call seamounts, these high points in the ocean floor, as well as even possibly a little canyon or trench occurring along there too. So satellite allows us to get even a more detailed picture of what is going on in the ocean floor. And as you can imagine, it is also a quicker way of looking at the ocean floor and mapping the ocean floor. There are many different systems out there, many different satellites that are orbiting the Earth, collecting data and sending it back to Earth. Some examples are the GEOStat from 1985 to 1990, the Topex Poseidon from 1992 to 2005. What the Topex Poseidon was, mapped the ocean surface topography and sort of the first major oceanographic research vessel to go into space. So it sits there, it orbits the Earth, and what it does is sending down thousands of radar pulses per second. And these measure the distance from the ocean surface to the satellite within a error of about 0.03 meters, which isn't that bad when you consider the great distances that it's traveling. But through the uses of satellites such as GEOStat and Topex Poseidon, we're able to accurately map the ocean floor. And there's other satellites that are out there from space that help measure the temperature of the ocean, the salinity content of the ocean, how much productivity the ocean is. So this remote sensing is a very valuable tool in examining the ocean and studying the ocean, not only the ocean floor, but other properties of the ocean. Here's an example of some of the data collected from the Topex Poseidon satellite. Once again, this has been processed. It's not the raw data. And it's just showing us different tidal heights at a certain period of time. And then finally, another satellite that's been used, and there's a whole host of other ones I haven't talked about, is the Jason 1, 2, and 3. Jason 1 and 3 are still in operation. Jason 2, issues with it, and it's no longer used. And what they do, these are successors to the Topex Poseidon mission, is basically their job is to measure ocean surface topography. So what happens is using an altimeter, it measures the hills and valleys in the ocean surface, so these slight variations caused by gravitational changes. Once again, these variations might not be something that we with our naked eye can observe, but they do exist. And this allows scientists to not only measure the topography of the ocean floor, but they can also look at how ocean currents move and look at how global ocean circulation occurs. So those are some of the methods that we have for looking at the ocean floor, determining what the ocean floor looks like and what the ocean basins themselves looks like. What we do is we take sonar data, the multi-beam and the side scan sonar data. We take data from satellite images, and from that we can develop a picture of what the ocean floor looks like or what the ocean basins look like. And we find that it might be a lot different from what you picture it. Some people imagine that might be a great big smooth bathtub with green slime on the bottom. But what we see is that a lot of the landforms that we see on land, mountains, valleys, hills, I know I've mentioned these already, we also see them on the ocean floor. Once again, the four things that we use to sort of help us study the ocean floor, know what the ocean floor looks like, know what the ocean basins look like, is we use sonar, we use submarine data, we use satellite, and we can also use seismic data, which I haven't talked about. So I kind of call them the 4 S's of looking at the ocean basin and the ocean floor.